Today, we want to focus on two different ideas or concepts. First, we want to talk about what an alternating series is and how to test for its convergence. Now, most of the series that we've been talking about so far had terms in the sequence that were eventually non-negative or positive. Now, this wasn't always the case. We saw with the convergence test that it did not require that the terms of the sequence eventually be positive or non-negative. But with the integral test and the limit comparison test, we were required that at some point, at least from there on in the tail of the sequence, that all the terms were non-negative or greater than 0. In that case, then we would chop off the head of the sequence, set it aside, and apply the integral test or the limit comparison test to the tail of the sequence. Now, when we're doing that, we're of course looking for whether or not the infinite series converges. Now remember, the infinite series, we've been talking about it like an infinite sum, but really what does that even mean? I mean, you're adding things together forever and ever. What does that mean? What it means, again, remember the definition of the infinite series is the limit of the sequence of the partial sums. So really the infinite series is the limit of the sequence of partial sums. So what we're going to talk about today are sequences that are different from some of the ones we've been looking at previously. These would be sequences where the signs are alternating in successive terms. So positive, negative, or they could start negative, positive, negative, positive. We call these alternating sequences. Now, it's not required, again, that the head of the sequence be alternating, but at some point, the tail forevermore must be alternating in sign. And then again, we chop off the head and set it aside, and then we focus on the tail of the sequence where it's following that alternating sign pattern. That's the thing that we want to talk about in this video. The second major concept from this section is what's called absolute convergence and conditional convergence. Now you can imagine if you have an alternating series, then every other term is going to be negative, which must mean that it's pulling the value down. Because every other one is negative, it's decreasing the limit of the sequence of partial sums. Now, if we were to take the absolute value of it, that would strip out all the negatives, and we call this absolute convergence. If we take the absolute value and it still converges, then we'll call that absolutely convergent. But it does turn out, because taking the absolute value produces larger values, always non-negative, that sometimes that does not exist, that it does in fact diverge, but the original sequence, where at least some of the terms were negative, does converge, and we would call that conditional convergence. So you can see how the idea of absolute convergence and conditional convergence relates to the idea of an alternating sequence and series. So we'll be taking a look at convergence and absolute convergence and conditional convergence in the next video. Let's go ahead and let me share my screen with you, and we'll focus on alternating series. Let's go ahead and talk a little bit more about how an alternating series might come about. Remember that in an alternating series, the odd subscripted terms and the even subscripted terms have opposite sign. One of them's positive, one of them's negative. So it's either positive, negative, or negative, positive. Now again, if the head of the series, the beginning of the sequence, doesn't follow that pattern, we chop it off and set it aside and focus on the tail. Only the tail determines convergence. The head will determine what the sequence of partial sums converges to, but it is the tail that determines whether it converges at all. Now, there are some different ways that we can achieve this alternating sign behavior. The most obvious is to take -1 and raise it to the index power, -1 to the n. But you can also sometimes get it to start with a different sign by raising -1 to the n plus 1 or -1 to the n minus 1. These generally have the same effect because they're 2 apart. We can also, however, achieve an alternating sequence by including a sine or a cosine function, but not just any function. We can include cosine of pi in the summand. Now, what is that going to do? Well, we know that the cosine of 0 is 1 and the cosine of pi is -1, and the cosine of 2 pi is 1 and the cosine of 3 pi is -1. So it alternates between 1 and -1. So by including the subscript, the index here multiplied by pi, we get this alternating behavior for the cosine of pi n, or n pi. We can do a similar thing with sine, but remember, sine alternates between 1 and -1 at multiples of pi over 2 and 3 pi over 2. So we need odd multiples of pi over 2. So to guarantee we get an odd value, we double n, which makes it even, and then add 1, which guarantees that it's odd. So 2n plus 1 times pi over 2 will guarantee that we have either a multiple of pi over 2 where sine is +1, or a multiple of 3 pi over 2 where sine is -1. And again, we could write this as 2n minus 1 as well, and that would also guarantee that it would be odd and it would generate, again, alternating signs. So we can see that we have some different ways of creating this alternating sign behavior. Now we want to actually define what we mean by an alternating series. Remember, the series is when we take out the comma from a sequence and we replace the commas with plus signs. We talk about it like it's an infinite sum, but really it becomes the value of the limit of the sequence of partial sums. It's s sub infinity. So we take the limit of s sub n as n goes to infinity, and that gives us the value of the infinite series. So we have different ways of defining an infinite series here. In each of these cases, notice that the b sub n, the sequence part, the summand part, is separated from the alternating behavior part. Now, again, we could achieve the alternating behavior with that cosine function or that sine function. So it doesn't have to be -1 raised to a power. It could be the sine of an odd over times pi over 2, or it could be cosine of n pi. But the b sub n, the sum of the sequence here, we're considering the b sub n's to all be strictly positive. So we're separating that alternating sign from the terms of the sequence. So we consider the terms of the sequence themselves to eventually always be positive. Again, if the head of the series doesn't follow this pattern, we take the head off and then we use the part where it does follow the pattern, where every other term is cycling positive, negative, positive, negative. Now let's take a look at the harmonic series. And specifically, we want to look at the alternating harmonic series. So the harmonic series, remember, diverges. We proved this using the integral test. And we looked at this one. It's the sum from 1 to infinity of 1 over n. And so it's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 forever and ever. And we found that this must diverge. Now we want to talk about the alternating harmonic series, where the part back here, the b sub n, is the same summand we had in the harmonic series, 1 over n, but it's got this alternating pattern to it. So it's got this -1 to the n plus 1. Now, when we have -1 to the n plus 1, or you can write it as -1 to the n minus 1, they both work, you'll see that every other term is changing sign. So you have 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5, and so forth. So every other term is negative. Well, it makes sense that this includes lower numbers than this one does. So maybe, just maybe, it's possible that the sequence of partial sums will converge to a finite value, and we can say the infinite series of the alternating harmonic series converges. And in fact, it does. So what we want to do is prove now that the alternating harmonic series does converge. So in order to do that, we begin by splitting it into its even and odd terms. So we're looking at the odd subscripts and the even subscripts. So we're going to look at the sequence of partial sums for an odd value and then the sequence of partial sums for an even value. So we're going to look at S sub 2n plus 1, which is an odd sum of an odd number of terms. And then we're going to look at S sub 2n, which is the sum of an even number of terms. If both of those sequences converge, and they converge to the same thing, then the infinite series must also converge and to that value. So we're going to show that if we're looking at a sum of an odd number of terms and sum of an even number of terms, that they both must converge. Notice that multiplying the index value by 2 guarantees that it will be even, and then either adding 1 or subtracting 1 will always guarantee that it becomes odd. So we're going to express the sum of the first 2n plus 1 terms, this is an odd number of terms, with S sub 2n plus 1, which gives us 1 over 1 minus 1 over a half plus 1 over 3 minus 1 over 4. They're alternating in sign. And remember, we have to go until we reach a sub 2n plus 1. So here we have 1 over a sub 2n minus 1. So this is a sub 2n minus 1. This is a sub 2n, which is a negative 1 over 2n. And then our last one is 1 over 2n plus 1. And again, this is a partial sum, not the full series, but just a partial series. So we have the partial sum from 1 to 2n plus 1 of negative 1 to the k plus 1 over 1 over k. Notice I changed the index to k because I'm using n as part of the upper limit of summation. Now, we want to show that this sequence converges by using the monotonic convergence theorem, which says if it's bounded in monotonic, it must converge. So we're going to show that it's actually decreasing and that it's bounded below. Now, in order to do this, we have to do some manipulation of some terms. And you may at home think to yourself, I would never have thought to do that. Probably I wouldn't either. But again, this is something that took someone weeks and months to figure out, right? And we're learning it in just a few minutes. What we're going to start with down here is 2k has to be less than 2k plus 1, which is true provided that k is greater than or equal to 0, because we could subtract the 2k from both sides and we would get the true statement 0 is less than 1. So this is starting from the statement 0 is less than 1, which we know to be true. And then as long as k is non-negative, we add 2k to both sides. Well, actually, it wouldn't matter. We still end up with a true statement. Now, for our particular series, we started with k equal to 1 because we're looking at the alternating harmonic series. So we know that 2k will be strictly positive as long as k is positive, and 2k plus 1 is strictly positive as long as k is at least not negative. All right, so we want to establish that those two things are positive because we want to take this inequality that you see right here, and we want to divide both sides by each factor. So we want to divide by 2k, and we want to divide by 2k plus 1 on both sides of the inequality. We have to show that they're both positive to be able to do that without reversing the inequality symbol. And we saw this when we were studying the convergence test or the comparison test. So now what we have is 1 over 2k plus 1 less than 1 over 2k, provided that k is strictly positive. We don't want k to be 0 because then we have 0 in the denominator here. And then, of course, we can subtract 1 over 2k from both sides of the equation, and we get that negative 1 over 2k plus 1 over 2k plus 1 which are, of course, the last two terms in the sum of 2n plus 1, these two right here, that proves that they are negative. So this right here, by saying less than 0, what we've really done is we've shown that this is a negative value. Whatever it is, it's less than 0. Then we come up with a recursive definition for S sub 2k plus 1. Now remember that you get from one partial sequence or one partial sum to the next by adding on the next term. So if I start with S sub 2k minus 1, and I then include the next term, which is negative a sub 2k, and the term after that, positive a sub 2k plus 1, that should give me S sub 2k plus 1. And this is a recursive definition because I've got to know the partial sum 2 in front of it in order to know what S sub 2k plus 1 is. But by definition of the alternating harmonic series, a sub 2k is negative 1 over 2k. Remember, we have that alternating sign behavior. And a sub 2k plus 1 is a positive 1 over 2k plus 1. But we just proved that these last two terms are definitely negative. So we have S sub 2k minus 1 added to a negative value, which must be less than S sub 2k minus 1. It's got to be less than itself because this is negative. So we're adding a negative value to it. It's got to be less than S sub 2k minus 1. Then we can take the far left and the inequality on the far right, and this basically means that S sub 2k plus 1 has to be less than S sub 2k minus 1, or you can move the S sub 2k minus 1 to the left. And note that you've shown that one of the later partial sums is smaller than the one in front of it, which must mean that the sequence of partial sums is in fact decreasing. So we've shown that this partial sum, S sub 2k plus 1, is a decreasing sequence. Now we need to show that it is bounded. If it's decreasing, it's going down in value. So we're not concerned with an upper bound, we're concerned with a lower bound. We don't want it to go to negative infinity. So we need to find a lower bound for it. We start by writing out some of the terms of S sub 2k plus 1, and we'll group them in pairs. So again, this is just the alternating harmonic series, but only up to a sub 2k plus 1. Notice the last term over there doesn't get paired up with anything, but all of these do. Now, if you're paying attention, you know that 1 is bigger than 1/2. So 1 minus 1/2, this must be a positive number. And you know that 1/3 is bigger than 1/4. So 1/3 minus 1/4 must also be positive. Likewise, 1/5 is bigger than 1/6. So that must be a positive difference. And 1/7 is bigger than 1/8. So that must be a positive difference. And we previously showed that these two right here in the other order came out one way. So now we know that this must be, in fact, positive. So we've got a positive plus positive, positive, positive. What about this last term that didn't get paired up? Well, k we know is starting at 1. So 2k is definitely positive. So 2k plus 1 is positive, which means basically it's positive 2. Which must mean that S sub 2k plus 1 is strictly greater than 0. In other words, it's decreasing, but it never goes below 0. So it's bounded below by 0. That means that we've shown that it is bounded and monotonic. So by the monotone convergence theorem, it must converge. Now, we've not said what it converges to. We just said it converges, but I haven't said what to. Now we want to look at the sequence of even terms. So we want to take a partial sum for an even term. So we guarantee that it's even by multiplying by 2. So S sub 2n. So we're not going as far out as we did previously. We're not going to a sub 2n plus 1. We're going to stop at a sub 2n. So when we get out here, again, we're taking a partial series, partial sum, and we're going out only until A is A sub 2n. We also want to show that this sequence converges. We're trying to show the alternating series converges. And we're going to show that the even one converges, the odd one converges, and then we'll show that they both converge. And that must mean that the alternating series converges. So again, we want to show bounded and monotonic. This time, we're going to show that it's in fact increasing and bounded above. So it's going up in value, but it's got a ceiling on it that it can't get above. So it must converge. We start with some of the basic things that we started with last time. We need to prove, of course, that 2k is greater than 0 and 2k plus 1 is greater than 0, so we can do division by them. And actually, we need 2k minus 1 to be greater than 0. We start with 2k minus 1 less than 2k, which is definitely true since negative 1 is less than 0. That's the true statement that we're starting at. Negative 1 is less than 0. Adding 2k to both sides still makes it true. So that's definitely true. Now, can I divide by 2k minus 1? Well, as long as k starts at 1, from 1 to infinity, then 2k minus 1 will be strictly positive. So I am allowed to divide both sides by both 2k and 2k minus 1, which leads to this inequality that you see here. 1 over 2k has to be less than 1 over 2k minus 1, which is true provided that k is strictly positive. Again, we don't want 0 in the denominator there. Notice that the smaller the denominator, the larger the fraction. So even though this is 2k minus 1, that makes the denominator smaller, which makes the whole thing larger. Now we know then by subtracting the 1 over 2k from both sides, that this means 1 over 2k minus 1 minus 1 over 2k is strictly positive. And notice that this corresponds to the last two terms in the partial sum. So when we're looking at this, we're looking at the partial sum s sub 2n, and we've just shown that the last two are strictly positive. Now we want to do something similar to what we did last time. We're going to write a recursive formula for s sub 2k based on s sub k minus 2. So that's 2 in front of it, right? So you have to add on 2 more terms. So the next one would be a sub 2k minus 1. And because it's an odd subscript, it carries a positive sign. And then you need to add on the next term, which is a sub 2k, which is as high as we're going. And because it has an even subscript, it carries a negative sign on it. So s sub 2k is defined recursively in terms of s sub k minus 2. Now, we know what the definition of a sub 2k minus 1 is. It's 1 over 2k minus 1. And we know what a sub 2k is. It's 1 over 2k, and it's a negative term. But we just proved that this combination of terms is strictly positive. So we have s sub 2k minus 2 plus a positive value, which has to be bigger than s sub 2k minus 2. So again, taking the far left, s sub 2k, and the far right, greater than s sub 2k minus 2, we get that the later partial sum is larger than the previous partial sum. And this proves it for the formula because I didn't specify what k was. So it's true in general for all values of k. This demonstrates that it is in fact increasing. This is one of our conditions for increasing. So we have an increasing sequence. This sequence of partial sums, s sub 2k, is going up in value for different values of k. I need to show it has an upper bound, that it's got a ceiling that it knocks up against and can't cross. Bounded plus monotonic means that it has to converge. I've got monotonic, it's increasing. I need to show bounded. So we do a similar thing where we group pairs of terms, but this time we take the first term and we don't pair it up. So we leave the 1 over 1 out. And then we have negative a half plus 1/3, negative a fourth plus 1/5, negative 1/6 plus 1/7, and so on. Now, notice that we didn't pair the last two terms together. Those would have been positive, but we did the second and third to last term paired together, and then the last term is by itself as well. Notice that 1/2 is definitely larger in absolute value than 1/3. And since it's negative, negative 1/2 plus 1/3, this must be a negative value. And the same is true of the next pair of parentheses, and the next pair, and the next pair. In other words, all those pairs of parentheses must come out to be negative terms. And we can also see that this last term is definitely negative because it's -1/2k. That means that what we have is the number 1 at the front plus a negative, plus a negative, plus a negative, plus a lot of negatives. So if we start with 1 and we add a bunch of negatives to it, we've got to be getting something less than 1. So this means that S sub 2k plus 1, taking the far left and the far right, it means it's bounded above by 1, the constant line, horizontal line, y equal 1. So we'll take a look at the plots in a few minutes, and you'll be able to see that, in fact, the even ones are bounded above by 1. So what have we done? Well, we've just shown that S sub 2k is bounded in monotonic. So by the monotone convergence theorem, it must converge. So again, I'm not saying what it converges to, which is a little bit of a problem because we need them to converge together to the same thing to prove that the alternating harmonic series converges. So far, all I've got is they both converge, but I haven't proved they converge to the same thing. So to prove convergence of the alternating series, that's the thing I need to do now. I need to show they converge to the same value. So we're going to put it together, and we're going to think about what it means to have S sub k plus 1. Well, that's the previous partial sum, S sub 2k, plus the next term, A sub 2k plus 1, which is 1/2k plus 1. And so we have this relationship between the two. Now we can take the limit of both sides of that equation, the limit of the left and the limit of the right. And we know that taking the limit as k goes to infinity should give us S infinity, whatever that comes out to be. And so I have the limit of S sub 2k plus 1 must be the limit of this sum, S sub 2k plus the next term out. But the limit of a sum is the sum of the limits, so I split that up. But the limit of this second term as k goes to infinity, I know that goes to 0. So I have right here that this part goes to 0, which must mean that I have the limit as k goes to infinity of S sub 2k plus 1 equal to the limit as k goes to infinity of S sub 2k equal to one another. And they have to be, of course, the value of the infinite series S infinity. So both sequences have the same limit. We need to make sure now S infinity is in fact finite. So it must be, because we know that each of these series converges to a finite value by the monotone convergence theorem. So in essence, we are done. We have proved that the alternating harmonic series does converge. Now, there are other techniques far more advanced than what we're going to be using in class that can show that the alternating harmonic series written in this format, 1/1 plus 1/2 plus 1/3 minus 1/4 plus 1/5, adds up or converges, the sequence of partial sums converges to the natural log of 2. So that's the value of S infinity. So when we're thinking of it, remember that it's not really a sum in the sense that you add things together when you have a finite number of things. It is, in fact, the limit of a sequence of partial sums. So it's really a limit value, which may mean you never actually quite get there. All right, let's take a look now at what the alternating harmonic series looks like on the plot, along with the sequence of partial sums. So here is our series up here, and we've got a table down here. And when we're looking at this, we have the harmonic series, the alternating harmonic series here in the orange dots. And you can see the divergence test, of course, that the sequence has to go to 0. And in fact, it does. You can see that they're getting closer and closer to 0 as it goes out. Now, what about the sequence of partial sums? Well, this up here, of course, is S1, and we have S2 and S3, S4, and so forth. So we can see right here that we have the odd sums decreasing, but bounded below by 0. And we can also see that we have the odd or even partial sums below and increasing and bounded above by 1, which is what we showed. But in fact, they're both bounded by natural log of 2. And we can see these partial sums alternating above, below, above, below, above, below. So this right here, of course, is S1, and this is S2, and this is S3, and this is S4, this is S5, and this is S6. So you can see that the odd ones are decreasing, bounded below by 0, and the even ones are increasing, bounded above by 1. And in fact, they are converging together to the natural log of 2 when written in that format. Okay. Let's now talk about what the alternating series test for convergence actually is. We're going to assume that we have some series that for some value of n greater than uppercase n, the tail of the series begins to alternate. Sorry about that. So we have an alternating series. So we've got some -1 to the n, or -1 to the n plus 1, -1 to the n minus 1, something like that. So again, if the head of the sequence does not match the pattern of the tail, we take the head off, set it aside, and we focus on the tail where it follows this alternating pattern. Now, in doing that, we want to strip the negative alternating pattern away from what's left in the summand, and we want that summand, at least from the tail out, to be strictly positive. Now, these are the conditions in order to apply the alternating series test, that at some point, these b sub n's are positive, discounting the -1 to a power. We also need it to be decreasing. In other words, b sub n plus 1 has to be less than or equal to b sub n. It has to eventually be a decreasing sequence, and eventually they've got to be positive alternating in sign. We also need to make sure that the limit of b sub n goes to 0. In other words, we still want to check the divergence test and make sure it doesn't diverge by the divergence test. If we have these conditions met, that at some point the b sub n's are positive, they're decreasing, and the limit of the sequence goes to 0, then we can say that it converges by the alternating series test, right? If the terms are eventually non-negative and eventually decreasing, but the limit of the sequence doesn't go to 0, then obviously it diverges by the divergence test. If the terms are eventually non-negative and the limit of the sequence goes to 0, but it's not eventually decreasing, then the alternating series test is inconclusive. We don't have a conclusion, right? So again, remember that there are 3 ways of showing that something is decreasing. We can show a sub n plus 1 minus a sub n is negative, right? The further out the term is, it's smaller than the one in front of it. We can show that a sub n plus 1 divided by a sub n is less than 1. Again, that means a sub n plus 1 has to be less than a sub n. Or we can show that the first derivative test applies, where the first derivative is less than 0, and that means it's decreasing, okay? Now, we need to make a few comments here about the alternating series test. Now, there are a few things to note about the alternating series test. First, remember that we're stripping the alternating behavior away from the rest of the sum end, and we're considering the rest of the sum end to eventually be all positive terms. So we're separating the terms of the sequence from that alternating sign. Note that the test can tell you about convergence, but it really doesn't say anything about divergence. In other words, your conclusions from the alternating series test are either it does converge because it meets the three conditions, therefore it converges, or it diverges by the divergence test, or you don't know, it's inconclusive. It doesn't meet all three of the conditions. So if any condition fails to be true, you don't need to check the other two. You can stop right there, right? If you can't show that at some point the tail is decreasing, you can't use the alternating series test. If you can't strip the alternating sign from the tail of the series and show that those other terms are always positive or at least non-negative, then you can't apply the alternating series test. And again, it's got to pass through the divergence test. If the limit of the sequence of the strictly positive terms doesn't go to zero, then it's not possible for it to have a finite value. So again, if any of the three conditions fails to be true, just stop, because you can't apply the alternating series test. You do need to verify all three conditions. Once you've verified all three conditions, there's not really anything to do. It's not like the limit comparison test where you had to take the limit of the ratio of an unknown sequence to a known sequence. There's nothing to do. If you meet the three conditions, it converges. That's the test. So as long as it meets the conditions, you're essentially done. Let's take a look then at example number 1, and let's go through and show how it meets the different conditions so that we can decide whether or not it does in fact converge by the alternating series test. Again, our choices with the alternating series test are it converges, we don't know, or it diverges by the divergence test. So first thing we want to check is, are the B sub n's eventually positive? B sub n's eventually greater than or equal to 0. So in this particular case, we're starting with n equal 1, and notice that the alternating behavior is given by the -1 to n plus 1. So B sub n is 1 over 7 plus 2n. So B sub n is equal to the sequence 1 over 7 plus 2n. And that is going to be strictly positive for all n values 1 and greater. So yes, we've established that it is. Why? Well, because in fact, n is greater than 1. So 2n has to be greater than 2. So 7 plus 2n has to be greater than, well, 9, which is greater than 0. So we've shown that it is strictly positive. And of course, the numerator is positive, and so a positive divided by a positive is positive. So we started with something that we knew to be true, and we built the denominator, and we proved that it was strictly positive. It's bigger than 9, so it's definitely bigger than 0. So it's positive, right? So first part is done. Second part we want to take a look at is we want to make sure, and probably we should have done this first, we want to make sure that the limit of the sequence does go to 0. In other words, we want to make sure that it is inconclusive for the divergence test. So we take the limit of the sequence. So we take the limit as n goes to infinity of the sequence 1 over 7 plus 2n. But you know, as n goes to infinity, the denominator is blowing up to infinity. So we get a constant 1 divided by something that's getting larger and larger, which drives the result down to 0. So we know that it meets the second condition. And then we want to take a look at the third condition, which is decreasing. And again, it doesn't have to be decreasing at the head, but at some point it's got to be decreasing. Now you can do this in different ways. You can show that a sub n plus 1 minus a sub n is negative. You can show a sub n plus 1 divided by a sub n is less than 1, or you can apply the first derivative test. Any of those will work. In my case, I decided that I was going to go ahead and write this as a function. So I'm going to think of this as f of n equal to 1 over 7 plus 2n, which I'm then going to write as 7 plus 2n to the negative 1 power to make it easier to apply the power rule for derivatives. So when I apply the power rule for derivatives, and I'm looking for f prime of n, I get negative 1 times the parentheses raised to the negative 2 power, decrease the power by 1. And then I have to apply the chain rule and multiply by the derivative of the inside function, 7 plus 2n. So I get a 2. So when I rewrite this with the parentheses dropped to the denominator, I get a negative 2 over 7 plus 2n quantity squared. Well, anything squared is definitely not going to be negative. So this is not negative, but the numerator is negative. And that proves that f prime of n is less than 0 for all values of n greater than equal to 1, which means it's decreasing. Therefore, I'm done. And I should go ahead and write the conclusion out. I'm a little bit out of space, but let me create a little bit of space here. I took up too much space there. Let's see if I can get this to go. And I'll copy that. And put it here. Thus, thus, by the alternating series test, the series from n equal 1 to infinity of 1 over 7 plus 2n with a negative 1 to the, was it n plus 1 or n minus 1? N plus 1 converges. Right? So again, applying the alternating series test is really just a matter of checking the 3 conditions. And usually the first 2 conditions are pretty straightforward. I mean, you can almost eyeball it and go, oh yeah, they're positive. Oh yeah, that sequence goes to 0. It's the third one that requires a little bit of work. But again, you do need to at least state it, all right? That yes, they're positive. Yes, the sequence goes to 0. And then prove that it's decreasing. Let's take a look now at example number 2. So we want to look at example 2, which is rather different from example 1. We do have something that is polynomial in behavior in the denominator, but the numerator is exponential. We have a base of 3 raised to a power 2n minus 1. It is alternating because of the negative 1 to the n plus 1. So I want to check and see if it meets the 3 conditions. So I'm going to start with the divergence test. So, which is probably what I should have started with the last time. I want to show that the limit as n goes to infinity of the b sub n, does that goes to 0. And of course, my b sub n here is 3 to the 2n minus 1 over n squared minus 1, right? So that's my sequence, stripping off the alternating behavior. Remember that we want to take the tail where it's alternating, and we want to strip off the alternating behavior so that the part of the sequence is just strictly non-negative. Okay, so when I'm looking at that, I need to take the limit as n goes to infinity of this exponential function in the numerator divided by n squared minus 1. Now, if you're thinking of the relative growth theorem, you already know what the result is going to be. All exponential functions grow on an order of magnitude larger than any algebraic function. And because that's true, we know that this is going to go to infinity. Now, in order to prove it, you would need to use L'Hopital's rule. Of course, 3 to the 2n minus 1, of course, it looks like this. So it's an exponential, so it's going to infinity, and n squared minus 1 is a parabola. It looks like this. So it's going to infinity. So we have the form of infinity over infinity. So we can apply L'Hopital's rule. Now, I hope you remember how to take the derivative of an exponential where the base is an e. Remember that you do still get the exponential, so that's not going to change. We still have 3 to the 2n minus 1. We also have to multiply by the natural log of the base, which is 3. If it were e, the natural log of e is 1. That's why it doesn't show up. And then we have to multiply chain rule by the derivative of the power. So then we also have a 2. So maybe I should put this natural log of 3 in parentheses, and then we have a 2. What about the denominator? Well, I get 2n. Well, the natural log of 3 is a constant, and so is the 2. So the 2 cancels the 2 and the n in the denominator, so those guys are gone. And I can pull the natural log of 3 to the front since it's just a constant anyway. And this gives me the limit as n goes to infinity of 3 to the 2n minus 1 divided by n. Now again, 3 to the 2n minus 1 is exponential, so as n goes to the right, it goes to infinity. So that's definitely infinity. And n is a linear function going through the origin, and again, as n goes to infinity, it goes to infinity. So I have infinity over infinity again. Oops, and this should be multiplication, not equals. And then I can apply L'Hopital's rule again. So I have a natural log of 3 at the front, and I'm going to apply L'Hopital's rule. So I'm still taking the limit as n goes to infinity. I've got this 3 to the 2n minus 1 again. I've got a natural log of 3 again, and I've got another 2 again, all divided by 1. Now, the natural log of 3 and the 2 are constants. They'll come to the front. If you want to think of it that way, you can write it out longhand. So you have 2, and then you have 2 natural logs of 3. So natural log of 3, quantity squared, times the limit as n goes to infinity of 3 to the 2n minus 1. Oops, lost my 2. There we go. But you know what that is. That's infinity. It's exponential. As it goes to the right, the y value goes up forever. So we have 2, the quantity natural log of 3 squared times infinity, which is still infinity. Now, this is only one of the 3 conditions to apply the alternating series test, but it failed. I can stop. I cannot apply the alternating series test. It failed one of the conditions. Just stop the alternating series test. In fact, because this is the divergence test, we can now say that this diverges by the divergence test. And again, the colon followed by the period stands for therefore, or hence or thus, but therefore is the normal translation. Therefore, the series n equal 1 to infinity. Make sure I've got it. 3 to the 2n minus 1. Oops, did I have n squared plus 1 and I wrote minus 1? I should make all those plus 1s. Sorry about that. I wasn't paying attention. So we have negative 1 to the n plus 1 times 3 to the 2n minus 1 over n squared plus 1. Of course, the plus 1 minus 1 doesn't affect it at all because when I apply L'Hopital's rule, that term drops out the very first time. So it doesn't make any difference in the result. Therefore, this series diverges by the divergence test, not by the alternating series test, but by the divergence test. If the limit of the sequence doesn't go to 0, it can't possibly converge. The sequence of partial sums can't converge to something finite. Now let's go ahead and take a look at another one. This next one is going to introduce a function type for you that is a little bit different than what you've seen before. So I want to create a little bit of space here. So this is the factorial type function. Now, factorials are fascinating things. I love working with them. They're actually a lot of fun. In the next section, we'll be studying the ratio test and the root test. And the ratio test in particular gets used all the time with factorials because some of the other tests, they're not really ideal for it. Limit comparison also works really well with factorials. So those two tests are great for factorials. How do you know it's a factorial? And for those of you who are like, I have never seen an exclamation point in a math class before, what is that? This is a factorial. So n factorial, what does n factorial mean? Let's do a quick tutorial in what n factorial is. 3 factorial means start at the positive integer 3 and multiply by all the positive integers below it till you get to 1. So it's 3 times 2 times 1, which of course adds up or becomes 6, right? What about 4 factorial? Well, that would be 4 times 3 times 2 times 1. But actually, that means it's 4 times 3 factorial. So I can think of it as 4 times 6, which gives me 24. And you can see that these factorials, they're growing pretty quickly. If I do 5 factorial, I'm going to end up with 5 times 4 factorial, or 5 times 4 times 3 times 2 times 1, which is going to come out to be 120. They grow incredibly fast. 6 factorial is 720. I don't remember what 7 factorial is, but it's quite large. As a class of functions, these grow faster on an order of magnitude than exponentials. So they'll overpower exponentials and pull it in that direction. So when you think about the relative sizes of different types of functions, natural log, they're the slowest growing functions that do go to infinity. And then you have natural log times algebraic, and then you have algebraic alone. That would be add, subtract, multiply, and divide, raise to powers, and take radicals. And then you have the exponential functions, then the factorials, and what we call tower functions. Tower functions, we may not see for a little bit. They have the index in both the base and the power. So they're not like polynomials where the power is a constant, and they're not like exponentials where the base is a constant. They have the index in both the base and the power. They grow faster than any other class of functions that we know of. So we know that factorials grow incredibly fast. Now we're looking at this sequence right here. We want to know, does it converge? And we see that it's got this alternating behavior. So we're going to try the alternating series test. And this means that our sequence of non-negative terms must be given by 1 over n factorial. Now, I need to give you a little bit more about factorials so that you can divide them when you get to that point. So what would n factorial be? Well, it would be n times the 1 in front of it, which is n minus 1, times n minus 2, times all the way down to 5 times 4 times 3 times 2 times 1, supposing that n was large enough that n minus 2 was bigger than 5. And you would get something like this. But because it is written this way, I can do a similar thing to what I did over here with the constants. And I can say that n factorial has to be n times n minus 1 factorial. Because n minus 1 factorial would not include the n factor, but it would have all the rest. So n times all the rest does give me the original. Or I could write it as n factorial equal to n times the quantity n minus 1 times n minus 2 factorial, because that would give me all the ones from here to the bottom, right? So this is how we work with factorials. Now we need to get back to our series. Our series is the alternating series, -1 to the n plus 1 times 1 over n factorial. We have three conditions to prove the alternating series test. We need to claim that the B sub n's are at least at some point non-negative. Well, that's obviously true. One thing I didn't tell you that I should tell you. By definition, 0 factorial is the number 1, right? So 0 factorial is not 0, it is the number 1. 1 factorial is 1 and 0 factorial is also 1. And that's by definition. There's no way to prove it. We just said this is so to make all the other formulas work. So definitely B sub n is going to be strictly greater than 0 for n greater than 1 because I'm multiplying by constant positive factors. So I'm testing again, are the B sub n's eventually greater than 0, right? Or at least greater than equal to? And the answer is yes, for n greater than equal to 1, n factorial is greater than equal to 1, right? So if n is greater than or equal to 1, n factorial has to be greater than or equal to 1. And 1 is greater than 0, which shows that it's non-negative. Now, that's the first one. The next one that we need to prove is the limit, right? Now, this one takes a little bit more hand waving. This is the divergence test. We want to show that the limit of the sequence B sub n goes to 0. So we have the limit as n goes to infinity of 1 over n factorial. Now you may go, oh, how do I do that? I can't do L'Hopital's rule. No, you can't, but you don't need to. This denominator is getting larger and larger and larger, and the numerator is a constant. This isn't an indeterminate form. This is a constant divided by something that's going to infinity. So this must go to 0. So we've got the first two conditions met. And again, it's mostly a matter of stating them or giving some small proof. It's not usually a lot of work. And then we have the next one, which is going to be the one where we need to show some more work. We need to show that the B sub n's are eventually decreasing. Here's where we come into a bit of a snag. There is no derivative defined on the factorial function. Sorry, you can't take the derivative of it. We can't integrate it directly either. So there is no derivative, so there can't be an antiderivative. So forget even going that route. But we do have two other ways to prove that this is a decreasing sequence. So our two ways of showing it's a decreasing sequence is to show that, well, let's use B sub n plus 1 minus B sub n, show that that's less than 0. That's one option. My favorite would be B sub n plus 1 divided by B sub n is less than 1. So if I don't have the first derivative test as an option to show decreasing, then I'm probably going to choose this option right here, showing that the ratio of successive terms with the after term being over the one before has to be strictly less than 1. Now I should be able to write that down. So let's go ahead and write down again what our sequence is. B sub n is equal to the sequence 1 over n factorial for n equal 1 to infinity. And we want to write down B sub n plus 1. And we want to divide that by B sub n, and we want to show that it is, in fact, less than 1. So I don't know if it's less than 1. I'm trying to prove that. So now B sub n plus 1 must be equal to 1 over, replace the n with n plus 1 factorial over 1 over n factorial. And I'm trying to show that that is less than 1, all right? This is what I'm trying to prove. Now, this gives me a complex fraction, which we've seen before. You get them all the time in the limit comparison test. And so now what we're going to do is we're going to simplify that, and we're going to take the denominator of the denominator and move it to the numerator. So this then tells me that I have n factorial divided by n plus 1 factorial. And I'm trying to establish, is that less than 1? Now, I can proceed a couple of different ways from here. I know n factorial is strictly positive, and I know n plus 1 factorial is positive, so I could move this to the other side. That's one possibility. But I could also reduce this, right? So let's take a look at what reducing this would look like. I can take this one and I can leave the smaller one as is and take the larger one and write it as n plus 1 times n factorial. Remember, n plus 1 factorial is equal to n plus 1, that last term, times the factorial that preceded it, n factorial. But notice then that I have n factorial in the numerator and denominator. And yes, you can see where I'm going with this. These are going to cancel. That doesn't mean it gets to jump up in the numerator. It's still in the denominator. And then, of course, because I know n is greater than or equal to 1, n plus 1 must be positive. So I can write that out here to the side. N is greater than or equal to 1. So n plus 1 is greater than or equal to 2, which is definitely greater than 0. So I can multiply both sides by it, and I get 1 is less than n plus 1. Okay, so far so good. Well, I've got a 1 on both the left and the right. You know where I'm going with this. We're going to subtract the 1 from both sides. I'm trying to get to a statement that I know is true. So I've got question marks on all of these. And the next one I'm going to write is 0 is less than n, which is definitely true because we're told that n begins at 1. So all of the previous inequalities must also be true, which shows that it is, in fact, a decreasing sequence. So I've met all three conditions. So then I can say, therefore, and I'm going to abbreviate this time, by the alternating series test, the series from n equal 1 to infinity of -1 to the n plus 1 times 1 over n factorial converges. It met the three conditions, therefore it converges, right? Our only options are it meets all three conditions, so it converges, or it fails the limit of the sequence going to 0, so it fails by the divergence test, it diverges, or one of the other two conditions doesn't hold, in which case we don't know. It could converge, it might not. We don't know, we can't use the alternating series test. So now let's take a look. We've got one more example that I want to work, and then we're going to talk about the remainder. It turns out that alternating series, like the integral test, are able to give us a very quick way, much faster than the integral test, of giving an upper bound on the error if you use the first n terms to approximate the infinite series. So we get an upper bound on r sub n very easily with the alternating series test. In that sense, it's better than the integral test. So before we get to that one, let's look at this one right here. Now this one I put in this particular set because it is a challenging problem and students were always just tanking this on the homework. So I wanted you to start looking at these, take 30 seconds and stare at it and say, gosh, can I get that in a different format that makes a little more sense? Can I make it into something else? Can I make it into a geometric series? Can I make it into a p-series? Can I make it into the harmonic series or the alternating harmonic series? So before you just blindly start applying tests, go ahead and see if you can rewrite this one. So I'm going to start now with the sequence part, not the alternating part, the -1 to the n plus 1. I'm going to start with this part. Notice that both are being raised to the n minus 1 power. Now, if one was to the n plus 1 power and one was to the n minus 1, I could pull two of them off and then they'd both be to the n minus 1 and I'd have two extras. In other words, I think I need to probably show you that. I have 2 to the n plus 1 over 3 to the n minus 1. I can rewrite this one as 2 to the second times 2 to the n minus 1 over 3 to the n minus 1. Notice that you're allowed to do that. When the bases are the same and you're multiplying, you add the powers, and 2 plus n minus 1 would give me n plus 1. So it's equivalent to this. And then the powers on the 2 and the 3 match, so that I can rewrite this one then as 4 times 2/3 to the n minus 1, right? Just a trick that we can do, a technique we can do to rewrite it. So I need to put my power over here, n minus 1. Well, gosh, this looks an awful lot like a geometric series, where the common ratio r is 2/3 between -1 and 1. But the problem is this alternating. Can I do something to actually get this to be geometric and not alternating? Well, I mean, it is alternating still, but an alternating geometric series. And the answer is yes. I can do the same trick I did here in the numerator here to the -1 to the n plus 1. In other words, I can split this and I can rewrite this as the infinite series from 1 to infinity of -1 squared times -1 to the n minus 1 times 2/3 to the n minus 1. Now, is that allowed? Yes. The bases are the same, both -1. So I add the powers. 2 plus n minus 1 gives me n plus 1. So these are equivalent. But what is -1 squared? It doesn't have the index in the power anymore. It's a constant. I know what -1 squared is. That's 1. And now I can rewrite this as the sum from 1 to infinity of -1 to the n minus 1 times 2/3 to the n minus 1. But notice that these powers match. This is an n minus 1 and this is an n minus 1, and they're being multiplied. They're both being raised to the same power. So I can put them together and multiply or raise the product to the n minus 1 power. So this then gives me -2/3 to the n minus 1. And in fact, that is a geometric series, right? We studied geometric series in the first section when we studied series in 5.2. This is a geometric series. And in this case, the common ratio r is -2/3, which we know is less than 1 and greater than -1. So we know, in fact, that it definitely converges. In fact, we know exactly what it converges to. We know that it has to converge to a first over 1 minus r. So we can go ahead and write down what S infinity turns out to be. So even though it looks like an alternating at first, and in fact it is alternating, but it's an alternating geometric series, I'm able to get the true value of the infinite series, or the limit of the sequence of partial sums. And this a first, well, what would a first be? Well, when n is 1, 1 minus 1 would give me 0. -2/3 to the 0 would give me 1 for a first. 1 minus, and r is -2/3. Notice that gives you a double negative. So that gives you 1 over equals, not plus. I'm thinking ahead. 1 plus 2/3, then you need a common denominator. And that, of course, is going to be 3/3 plus 2/3, which is 5/3. So you have 1 divided by 5/3, which becomes 3/5. And that is the actual value of the infinite series. So it definitely converges. We didn't prove it using the alternating series test. We used the fact that it was a geometric series. Granted, an alternating geometric series, but still a geometric series. And we're able to actually give the value of the infinite series. Remember, this is the limit of the sequence of partial sums. That's what the value of the infinite series is. we've been sort of thinking of it as like adding things together forever and ever, but really, what does that even mean? I mean, you can't really add things together forever and ever. What it really means is the limit of the sequence of that partial sum. Now what we want to talk about is estimating the size of an alternating series. In other words, we want to talk about if we use the first number of terms and we add those together, a finite number, then we can get an approximation for the infinite series, but we want to know how far off we are. We want to know the terms that we didn't include, how large might that be? What's our error? Okay, so remember earlier that we basically had S sub n plus R sub n has to equal S infinity, right? So this is R sub n, okay? So if I use the first n terms to approximate the infinite series, I'm not using the ones from n plus 1 out, and all of those will give me the value R sub n. And these two added together must give me the true value if it converges, right? Now, if we think about the alternating series test and we look at one that we know converges, so we're looking at the alternating harmonic series here. Remember that we saw that the sequence in orange dots is approaching 0. And we can tell that if we strip off the alternating sign part, the 1 over n, they're all positive. And we know that it's decreasing. We can take the derivative of 1 over n, which gives us negative 1 over n squared, which is always negative. So we know it passes, right? So we know that we have convergence by the alternating series test. And when we're looking at this, what we want to do is say we want to use S5 to approximate the value of the infinite series. Now, where's S5? Well, remember, this is S1 and this is S2. The black dots are the partial sums. That's S3. That's S4. And that's S5. So if I want to use that value right there to approximate the entire thing, I need to know what the error is. So that's what we're looking at right now. Okay, what would the error be? And notice that the error is coming from all the terms past the fifth one. 1, 2, 3, 4, 5. So this is A sub 1, A sub 2, A sub 3. I may be missing one. A sub 4. I think the first one is supposed to be up here somewhere. So after you chop off the fifth one, actually, I think A sub 1 must be missing. I must have eliminated it off of my screen. Is that right? Because the first one would be positive. Yes, the first one would be positive. So this is actually A2, A3, A4, and A5. So we need to know how much error all those other terms create. All of these other terms combined together give us the remainder, the error in using just the first 5 to approximate. And you can see right here that we're looking at the sequence of partial sums, and you can see the odd ones are decreasing towards the natural log of 2, and the even ones are increasing towards the natural log of 2. And we know from other techniques that are beyond our ability at this point that S infinity is the natural log of 2 when written in this way. Now, notice that S infinity, which is that blue dashed line here, is always in between each pair of successive partial sums. So it's between S1 and S2, between S2 and S3, between S3 and S4. But it's not always clear which one is on top and which one's on bottom. It's not always the same one. And the first pairing, S1 is above, S2 is here. And the second one, S3, is over S2. And then S3 is over S4, and the infinite sum is between, right? So we have this idea that between every pair, the infinite sum is either between Sn and Sn plus 1, or Sn plus 1 on the left and Sn on the right. So it's in between the two, all right? If we then take this expression and we subtract S sub n from all three parts, we get 0 less than S sub n, or S infinity minus S sub n. We know what that is, right? That's R sub n, which has to be less than Sn plus 1 minus S sub n. Or if it were in the other order, we get something similar. But because we don't know which sign, which one's on top and which one's on bottom, we can say that basically the difference between any two successive terms, which has to be greater than equal to R sub n, this is R sub n right here, we know that it's got to be less than equal to the difference between Sn plus 1 and Sn, either in this order or in that order over there. And if it's in between that, that must be the value of A sub n plus 1. Now that's a really startling idea. What does that mean? Let's go back up here. It means that if I use S5, this value right here, to approximate the value of the infinite series, which is really natural log of 2, but that's pretty darn close to natural log of 2. I'm only using the first 5. My A1 is missing. How do I know how big the error is? Well, it says if I use the first 5, go to the next term out, and that tells me an upper bound on the error. So I go to A6, which is the first one not used. And that value right there, the strictly positive value, not including the alternating sign, the strictly positive value gives me an upper bound on the error. So we have an upper bound for the error, which is A sub n plus 1, where we've stripped the alternating behavior from the expression of the sequence, stripped the negative 1 to n plus 1 from it. In other words, A sub n plus 1 is greater than or equal to 0. All right, so it's a positive term, which makes sense. It should be greater than or equal to the remainder. So it's bounded by the first unused term. Now, this is much simpler than what we did for the integral test, where our remainder was bounded between two improper integrals. We had the integral from n plus 1 to infinity, and then we had the integral from n to infinity, providing an upper bound, and the one from n plus 1 to infinity, providing a lower bound for that error term. So let's take a look now at example 5 and see how we can put an estimate of the maximum error if we use S5 to approximate the infinite series. Now, this is the convergent series we saw in example 3, so we don't need to go through and prove that it converges by the alternating series test. We've already done that. It definitely does converge. We want to approximate the infinite value of the infinite series with S5. So what is S5? Well, let's go through and find the value of S5. So when we're looking at S5, we're taking the sum from n equal 1 to 5 of negative 1 to the n plus 1, 1 over n factorial. So first, n is 1. So the signs begin with 1 plus 1, which is 2, so squared. So it starts positive. So we have 1 over 1 factorial, and then we have an alternating sign. So the next one's negative, 1 over 2 factorial, then positive 1 over 3 factorial, negative 1 over 4 factorial, positive 1 over 5 factorial, and we stop, right? We're taking the sum of the first 5 terms of the sequence. So when we look at this, we can write this out in terms of fractions. That's just 1. This becomes 1/2. 3 factorial, we said, is 6, so this becomes 1/6. 4 factorial is 24, so this is 1/24. And 5 factorial is 120, so we get 1 over 120. And when we add all of these together, we come up with 17 over 60, which is our approximation for the limit of the sequence of partial sums. It's our approximation for S infinity. So again, we're approximating S infinity with S5, but I want to know how wrong could I be? What's the error? Well, with an alternating series, the error is given by the first term you didn't use. And in this case, that would be A sub 6. So R5, the remainder, if I use the first 5 terms, better make that look more like 5, is less than or equal to A sub 6, n plus 1. So 5 plus 1 will give me 6. Well, what is A sub 6? Well, A sub 6, again, the A is only referring to the non-alternating part. So we have 1 over 6 factorial, which is equal to 1 over 720. So what does that mean? That means my approximation for the value of the infinite series is 17/60. And I could be off by as much as 1 over 720, but not more than that, right? So if I want to, I can get more accurate. Let's take a look now at what happens when we try to get more accurate. In other words, we don't know how many terms we want to use to approximate the convergent series. In this case, we just want to make the error be less than 10 to the negative 9. So we're looking for the n value that will give us an r sub n less than 10 to the negative 9. So we're going to start and we're going to write down our expression again. Now, again, this is the same sequence we had before, so we already know it converges by the alternating series test. So we know then that we have r sub, let's use an uppercase n to distinguish it, has to be less than equal to a sub n plus 1, which is equal to 1 over n plus 1 quantity factorial. And let's make that be less than 10 to the negative 9. If we make that be less than 10 to the negative 9, then I have that the remainder, the error, is less than 10 to the negative 9. So I'm going to focus on this right side with this expression that I have right here, and I'm going to try to find a value for uppercase n. So the first thing I want to do is write 10 to the negative 9 in its fraction form. So I have 1 over n plus 1 factorial less than 1 over 10 to the 9th power. Now, I know 10 to the 9th power is definitely positive, and my subscripts are starting at 1 and increasing. So uppercase n plus 1 must be positive. So n plus 1 quantity factorial must be positive. And if it's positive, I can multiply both sides of the equation by each of those factors. So I'm going to multiply both sides by 10 to the 9th times n plus 1 factorial. Now, what does this do for me? Well, this gets rid of the fraction part, which is always a good thing. So I got rid of that, and it puts the 10 to the 9th on the left-hand side of the inequality. And then I've got n plus 1 factorial on the right. Now, to finish this, you're actually just going to have to try some numbers and see what we get. Now, 10 to the 9th, that's big, right? So 10 to the 9th is basically a 1 followed by 9 zeros. So I need to get a number that's bigger than that. So I need n plus 1 factorial to be larger than 1 billion. So I start with some numbers and try them out. And I recommend, of course, that you use a calculator for this. It will save you a little bit of time. And on most calculators, they do have the factorial on there. So mine's right here above the 4-digit. So I'm just going to start with something like 6. If n is 6, then n plus 1 is 7. So how big is 7 factorial? So 7 factorial is 5,040. That's not nearly big enough. So let's bump the number up a little bit. Let's try 15. So 15 plus 1 would be 16. So what's 16 factorial? Whoa, okay. Well, 16 factorial is 2.09 times 10 to the 13th. So 16 factorial is equal to 2.09 times 10 to the 13th power. Well, 13, that's more zeros than I need. I only need 9. So let's come down some. Let's try 12, right? Something in between those values. So if I let n be 12, 12 plus 1 would give me 13. So let's try 13 factorial. Or you could try 12 factorial if you let n be 11. So for 13 factorial, I get 6,227,227,020,800. Sorry, I ran out of room. Okay, well, that's the right number of zeros. Okay, so definitely the 13 works. Would 12 work? If 12 is the factorial, then n would actually be 11. So let's try 12 factorial and see if that one works, because definitely 13 factorial is close. So let's try the 12 factorial where n is 11, and I get 479,001,600. That's not big enough. I need in the billions. So 12 factorial is not big enough. So 11 is not a big enough value for n. So I've got to use 13. If I use 13, then that means that n has got to be 12. So again, this gives me the number of terms that I need to find. So I have n plus 1 equals 13, which implies that n equals 12. So if I take the sum of the first 12 terms, I'm guaranteeing that the error is no more than 1/1,000,000th off, right? Which is incredibly close, right? So this is how we can find the value of the subscript to make sure that we meet a certain error condition, right? Let's take a look at one more example, which is example number 7. And it says find an upper bound on the maximum error if we use the first 10 terms to approximate the following series. What is the approximate sum in fraction form? And again, this is the same one that we did in example 4. It's actually a convergent geometric series. It does alternate in sign. So it is also an alternating series test or an alternating series. And we know that it converges, and I think we found it converges to 3/5. Isn't that what it was? You can check in your notes, but I think that was correct. Let's see if we can find it. It was example 4. So coming up here, yes, it converged to 3/5. So now what we want to do is we want to take the first 10 terms. So we're looking at S10, which is the sum from n equal 1 to 10 of -2/3 to the n minus 1. And I'm using that rewritten form because it'll be a little bit simpler. So when we're looking at this, this is not an infinite sum. So I can't use a first over 1 minus r. Do you remember the formula? You probably don't. So I'll write it down for you. The formula for a finite geometric series also has a first over 1 minus r, but it has another factor in the numerator. So the other factor in the numerator becomes 1 minus r to the n power, right? Remember, if r is between -1 and 1, as n goes to infinity, r to the n would go to 0, and that would give us a first over 1 minus r. But in this case, it's not going to infinity, it's stopping at 10. So a first, again, is 1. So we have 1 times 1 minus, and then we have -2/3 raised to the 10th power divided by 1 minus a -2/3. Now, we've already figured out from previously that the denominator becomes 5/3. So we've already done that work. We don't need to repeat it. We know then that 1 times anything is that thing, so we don't have to worry about that. So we've got negative 2/3 to the 10th. So the negative is going to disappear. So it's basically 2 to the 10th over 3 to the 10th, 1 minus that. And you can take your calculator and you can figure out what that comes out to be. And it eventually, if you get it written down correctly, you should end up with 58,025 divided by 59,049. Right? That's what you get in the numerator. Okay. Hopefully I did that correctly in my notes. And when you simplify the complex fraction and you reduce it, you end up with the following expression. This becomes 11,605 divided by 19,683, right? Which this turns out to be about 0.59. Now remember, the true value is 3/5, which is 0.6. This is a very good approximation. I'm very, very close. Now we want to know what the error is. So again, we use the first 10 terms to approximate the value of the infinite series, the limit of the sequence of partial sums. So our error from using the first 10 is that it has to be less than equal to the next term out, which is a sub 11. And again, this is going to be the one without using the alternating behavior. So this is going to be the 2/3 raised to the 11 minus 1 power. So we don't take the alternating behavior when we do the subscript there. So we have 11 minus 1. And this turns out to be 1,024 over 59,049. Note that that is the same denominators up there. That's not accidental. And this turns out to be roughly 0.017. In other words, I could be off by as much as 0.017, but no more than that. And in fact, I'm off by less than that because I know the true value is 0.6, and I'm exactly 0.01 off. But again, this is giving us an upper bound on how far off we could be. So let's say something in summary about the relative size of an alternating series before we get to the next video where we're going to talk about absolute and conditional convergence. When we think about this alternating series, we've got every other term being positive and every other term being negative, at least at some point in the tail. That must mean that this series, the sequence of partial sums, they're smaller than this one is right here, where they're all strictly positive. And so that must mean that if we're looking at this, and again, let's write out some of the terms so we can see it. We've got the alternating here where they're all positive values, and we've got the harmonic here where they're all positive, and the alternating here where every other one is negative. It must be that this one is smaller than this one. And in fact, that is the case. So an alternating series is always going to be smaller than the series we would get if we were to take the absolute value of the sum end. That does not guarantee that that will converge, of course. We'll have to take a look in the next video at what we mean by absolute convergence and conditional convergence to determine when the absolute value of something like an alternating sum end, when that converges and when it does not. I hope you will join me for the next video where we consider absolute and conditional convergence.